The second speaker is Yarin. He's from Ben Gurion University, also a master's student, at the same time also working at Akamai, and I think his slides will be coming up shortly. And he will be talking about ways to detect DNS exfiltration in real time. Your audience.
Hello, everyone. Really excited to be here to present my work on information-based heavy hitters for real-time DNS exfiltration, which I worked with Asaf Nadler and Asaf Shabtai from Ben Gurion University. Year after year, we see malwares using DNS protocol to exfiltrate data out of organizations. It can be compromised credit card details from point-of-sale machines, credentials, passwords, or cryptographic keys out of compromised enterprise machines. We continue to see this issue rising year after year. And this can be a bit surprising, as this problem is more than 25 years, has been discussed for more than 25 years. In fact, it was first described in '98. And it is a relatively highly researched topic with over 100 papers. So why is it not solved after so many papers are written on it? So there are three main reasons. One is that previous research rarely used large-scale, realistic, real-world data sets, which makes it very hard to infer if they're actually if their reported performances really has their saying. Previous research is rarely applicable in real time, meaning that there is data consolidation out to an external machine, which means that many hours may pass by the time that the attack is detected and mitigated. And the last point, which is related to the second one, is their very complicated implementations requiring complex models with a relatively large number of features extraction. So now I will go over a short demonstration of how a DNS exfiltration attack may work. So first, the attacker needs to somehow infiltrate the compromised endpoint, which can be done, for example, by luring the victim to go to a malicious website or download a malicious email attachment. And once the machine is compromised and the malware detects data that can be of interest to the attacker, for example, point-of-sale machines, it can be credit card details of customers. It starts to exfiltrate the data by prepending it to a DNS query that is targeted at a registered domain that is managed and owned by the attacker, in this example, attacker.com. And basically, they're taking advantage of the DNS resolution process. And the query basically propagates until it reaches the attacker.com authoritative name server, which is, as I said, operated by the attacker. And once the attacker gets the exfiltrated data, they may encode back a response, which reaches to the machine and can, for example, contain further instructions to the malware. So basically establishing a bidirectional covert communication channel over the DNS protocol. This can, for example, serve for command and control purposes. Yeah, and this is what a DNS exfiltration attack looks like. So in our paper, we propose a new novel method to detect DNS exfiltration, which can be run directly on the DNS resolver. So the main advantage that we offer is that it is applicable in real time. It can run directly on the DNS resolver. It won't impact the performance of the DNS resolution process. It offers inline speed processing of over 15 15 times faster than the current state of the art in terms of real-time DNS exfiltration detection from 2019. And it was done on a machine that resembles that of real DNS servers hardware. The second point is that we tested it on at scale on real-world datasets. The main dataset is 255 billion DNS queries dataset from over 750 real-world enterprise organizations protected by Akamai. And to the best of our knowledge, it is the largest ever evaluated. And we also performed the analysis on the largest public dataset of over 35 million DNS queries, which was collected from ISPs and open source DNS exfiltration tools were used to exfiltrate data. And the last advantage is the simplicity of it. This was the main thing that we were looking for. We were looking for a simple solution that can be implemented on standard DNS servers, such as Bind. And we are currently working on deploying it on Akamai DNS resolvers. And there's also the source code, which is open source. Yeah, so when we reviewed earlier works, we saw that queries that go through the DNS resolver are rarely ever being classified directly on the DNS resolver. And the main key for this is that DNS is a critical protocol which should not be slowed down. And for that reason, in previous works, they usually suggested an out-of-band classification, basically a system that needs to be run outside of the DNS resolver. You need to collect the data, consolidate it into this out-of-bound classifier, out-of-band, I'm sorry. Yeah, and this is the main thing that we wanted to change in this work. We wanted the classification to be directly on the DNS resolver without impacting its ability to resolve DNS queries. So the basic idea is very simple. We're basically performing the detection directly on the DNS resolver by the way of quantifying the amount of information that is suspected to be transmitted over the DNS protocol to every registered domain. So, and raise an alert if this amount exceeds some kind of a threshold. And there are two main challenges. It is that in order to do so, we need to collect all the DNS queries that are sent, because we're trying to count the amount of information that is transmitted. So we collect the unique queries, which can increase linearly in the number of DNS queries. And under an attack, this can be very overwhelming because we're expecting to see a lot of distinct DNS queries. So in order to resolve that, our approach was to perform an approximation of the cardinality, of the information cardinality. And we utilize for this the hyperlog log, a variation of the hyperlog log, which instead of solving the cardinality estimation, it solves what we call the information, the unique information estimation problem. And which in the case of DNS queries, the information is essentially the length of the subdomain. So a little bit more details. The ibHH algorithm contains of something that we call a cache. It is essentially a hash table that maps domain names to hyperlog log instances, or the variation of the hyperlog log instance, and a value which we call seed, which is an hash value that is applied to each DNS query. And whenever we see a DNS query targeted at some registered domain, we are calculating this hash function. And if it is lower than the current seed value of the domain, then we decrease it. And whenever we reach the capacity of this cache, because it is capped at k, which is the number of domains that we allow in this cache structure. We evict the one with the highest seed, because this one is the one that is least information heavy and is the least likely to be a suspected domain. And so for every DNS query, as I said, we quantify the amount of information, and we do it with the hyperlog, which can do the cardinality estimation because of the way it's structured. And the last thing is that we're resetting this cache every constant time frame, because we need it to reduce the threshold of entry. Yeah, and now I'll go over a short demonstration of how this works in action. So the main thing that we see here is that the algorithm runs directly on the DNS resolver. And whenever it processes a query, it searches for this, it extracts this subdomain and domain, which is the second level domain, and it searches for it in the cache, and if it's in it, we're adding it to the hyperlog log instance. So in this case, we're adding this subdomain to the hyperlog log of mail.com, mail for malware, and it increases the amount of information estimation by the length, or approximately by the length, so from 1993 to 1998. And in this case, you can see that the detection threshold is set to 1,000, so it's allowed because it's less than that. And now a new DNS query gets to the DNS gateway. We're once again adding it to the hyperlog log instance. And now, because we're exceeding this threshold, we're blocking the query. And we can raise alert to the SOC team. Yeah. So one of the problems with DNS exfiltration is that there can be benign uses to perform DNS tunneling, as described in the work of Nadler from 2 years ago. One of which is, for example, antivirus agents may send hashes of files to scan over the DNS protocol, and this looks a lot like DNS exfiltration. And there isn't really a way to really distinguish between those two kind of cases. So what we propose is using one method, which is basically you take a popularity list, for example, Tranco, which is a way to rank domains by their popularity, and another one, and this is not very unique, it's kind of popular in this field, or in cybersecurity in general. And the second is that it's what we call peacetime, wartime. We're essentially running the algorithm in the enterprise network for some time. We propose 1 day because we saw that more than 90% of the distinct domains are observed, that are observed over a week are observed in the first day. So this will enable us to compose a list of benign information heavy eater domains and collect them into an allow list. Another advantage of this method is that it's very comprehensible. So we're not really using a threshold which is on a scale of 0 to 100, which really can be explained. The threshold is essentially the number of bytes that need to be transmitted to raise an alert. So we can see that there's obviously a trade-off between the number of true positives and false positives. The lower you set the threshold, you're more likely to detect an attack, but it might come at the cost of a false positives. When we propose to tune it while you're doing the peacetime generation, to get like what you would refer to as an acceptable false positive rate. Yeah. So the evaluation is fairly standard. we're comparing the ibHH with 3 state-of-the-art methods over 3 datasets, which are either collected from Akamai customers or the open source dataset, which is the third one. And the evaluation is relatively standard. It is inspired by works from NADLA 2019 and DIAS 21. We're taking benign traffic and we inject realistic synthetic DNS exfiltration malware data into it in random spots, but based on the patterns that these malwares and tools work. And we measure the TPR and FPR for each method. We saw across the board that ibHH performed as good or better to other solutions, despite being able to run in real time and showing less false positive rate than other methods. We proceeded to do a longitudinal analysis on real-world traffic. Again, we ran the algorithm for 21 days over 750 enterprise organizations. Again, the Akamai dataset. And we were able to detect 2 real-world attacks. One is an open source DNS tunneling tool called yourfreedom.net. And the second is an attack that is a simulation of a DNS exfiltration attack that is done by a cybersecurity company, showing that it was basically a test and it was detected. The majority of the methods were able to detect it, but ibHH was able to do it with fewer false positives. So to conclude, I've discussed ibHH, which is a simple and effective real-time DNS exfiltration detection method designed to be deployed on DNS resolvers for real-time. And it shows state-of-the-art capabilities, despite being able to run in real time. As for future work, as I said, we're currently working on deploying it on Akamai DNS resolvers. And it's currently in beta testing. And we're doing, we want to continue the longitudinal analysis. Thank you. This QR code takes you to the source code if you want to run it. Yeah.
All right, let's thank our speaker. All right. So if there are any questions, again, come up to the microphone and state your name and affiliation while you think of some. Oh, there's somebody. Go ahead.
Hi, TJ from Virginia Tech. Thanks for the talk. I have one simple question. Is there any chance that you can publish the dataset, DNS datasets flagged as malicious?
Yeah, the datasets from Akamai, unfortunately, they're customer that can contain sensitive data. These cannot be published, unfortunately.
Right. Thank you.
Hi, Renaissance from UCI. So great talk. My question is it possible for the attacker to spoof their IP address so that when you are categorizing by the server name, it shows different server name?
Could you please repeat the question?
Yeah. So you are calculating the probabilities for server names, right? Specific server names. So is it possible to spoof IP address so that it shows different server name?
It's not based on the IP address. It's based on, we're doing the cardinality estimation based on the domain names themselves, not based on the IP addresses.
Okay, thank you.
Thank you.
Hi, Samuel Giroux, MIT Lincoln Laboratory. So if I understood right from your presentation, you're essentially using the straight length of the subdomain being queried to capture the amount of information being conveyed there. Did you look at using other methods of estimating the information in text?
Yeah, we tried both. We tried just the cardinality, and it wasn't performing well. And we also tried entropy, and it was performing well for like very noisy attacks, like those that are displayed by high throughput tunnelings, like iodine, which is intended for like web browsing, so it's very noisy.
Yeah.
But whenever like the attacker was trying to be very stealthy, like in the case of DNS, which is basically just command and control, it wasn't able to detect it.
Interesting. Thank you.
All right, so I'll take the final minute that we have and also ask a question. Isn't this kind of a cat and mouse game where essentially if I use a domain generation algorithm to just pick different actual registrable domains, right? And so essentially I'm hiding less information in the subdomain and I'm hiding additional information in the domain name. Because we were saying malware and this like, back in the good old days, you just have DGAs and you have different domains all the time. So how would that affect your system?
That's correct, because we're doing the we're basically doing aggregation by the domain name. So in the case that you're using like a DGA, it is indeed very likely that you will be able to, at least for, it really depends on the threshold, but it is possible that you will be able to bypass. One possibility is maybe to do like information estimation by like the customer, by the client endpoint, and then you might be able to find that the this endpoint is transmitting a lot of data. But then you won't be able to tell what is the domain that is being used for it, but you will be able to tell which machine is being is working maliciously. Anomalously.
I mean, fortunately, as we learned from Herbert's keynote, the scientific community and the hackers don't interact, so they will never learn about this. So let's thank our speaker again.
Thank you.